I'm Andrew, and today I'm going to tell you about a sort of different type of attack, which is an attack on time-triggered Ethernet networks. And this is work that I did in collaboration with my advisors, Ronald and Baris at the University of Michigan, and also Linh, Phan at the University of Pennsylvania. So time-triggered Ethernet, or TTE, if you're not familiar with it, it's a really popular network technology used in safety and mission-critical applications. So for example, it's very quickly becoming the de facto standard network technology used in crewed spaceflight. It's used in multiple NASA spacecraft, and it's also widely used in things like military aviation systems and energy generation systems like wind turbines. And one of the main reasons that people want to use time-triggered Ethernet is that it's a mixed criticality networking technology. So it allows designers to reduce size, weight, and power by sharing the same network, the same switches between both really critical devices, critical nodes, and non-critical nodes. So here in this example, I'm showing 4 different critical nodes. So these could be things like flight computers or power distribution units, the types of devices a system really needs in order to operate safely. And typically, these critical nodes will communicate over multiple redundant planes of the network or redundant channels for fault tolerance. But then hanging off of one of those redundant planes will be some number of non-critical nodes. So these could be things like the in-flight entertainment system in an aircraft, or in spaceflight, very commonly, it's a laptop used by an astronaut to conduct experiments when they're on a space station. And the TTE protocol is designed to provide complete isolation between these critical and non-critical devices. So in other words, no matter what a non-critical node does, it shouldn't be possible for it to interfere with the timing or successful delivery of these critical messages between, for example, the flight computers. And this isolation guarantee of TTE ends up being really important in practice. And the main reason for that is it's used as justification for a ton of different cost-cutting measures. So by far the biggest cost-cutting measure it enables is it allows designers to buy these non-critical devices from relatively low-cost or untrusted suppliers. So think commercial off-the-shelf devices. If I want to add a laptop to my space station, I don't have to design that laptop from scratch where I know each individual circuit component that goes into this thing. I can just buy it off the shelf, fly it up, plug it in, and I know no matter what it does, even if it's malicious, it can't interfere with any of my critical systems. Similarly, it's often used to justify relaxing security requirements for non-critical devices, and also just to not include these non-critical devices in things like safety reviews, which saves a ton of money and a ton of time. So in this work, which we call PCspooF, for protocol control frame spoofing, we introduced the first attack that's actually able to break these isolation guarantees of TTE, allowing just a single malicious non-critical device, which may be connected to just one of TTE's many redundant network planes, to actually disrupt critical traffic on all of the planes. And in the worst case, a single successful attack can actually disrupt all of the critical TTE devices in the entire network, regardless of where they're located. So here, when I talk about disruption, I'm talking about things like causing message drops, messages to be sent at incorrect, erroneous times, messages to arrive later than the deadline, later than when they were needed, stuff like that. Now, luckily, this disruption is temporary, but it can still be quite significant. So we've shown that each successful attack can disrupt devices for up to around a second at a time. And this also isn't just a once-in-a-blue-moon thing. So an attacker can perform this attack back-to-back on the order of every 10 to 15 seconds successfully in order to create as much mayhem as possible. And later in this talk, I'll show you that this sort of repeated disruption can cause even really sophisticated safety or mission-critical systems to fail. So the thing that makes this sort of attack even remotely possible, and in particular allows us to disrupt devices which are spread all throughout the network, is we go after the TTE synchronization protocol. So as the name time-triggered Ethernet would suggest, a TTE network only works if all of the devices are synchronized to each other. So if an attacker can somehow disrupt that synchronization, they can disrupt the critical traffic flows that rely on that synchronization to exist. And the way that we do that is we go after one aspect of the TTE synchronization protocol, which is a little bit brittle, which is that in order to maintain successful synchronization, that requires a certain trusted sync message, which is also called a protocol control frame, or a PCF. to be generated by specific switches in the network and then consumed at the end devices. And this particular sync message has a lot of power because if the contents of this one message are ever wrong, then just receiving that one wrong message is actually enough to knock you out of synchronization by making you detect a timing click is what's happening. And importantly, this works even if that bad synchronization message is only on one of the redundant network planes. It doesn't have to be on all of them. So that means that if an attacker could somehow inject a malicious version of this sync message into the network, they could cause devices to lose synchronization on purpose. And that's exactly what we do in this attack. So really the PCspooF attack occurs in two distinct stages. In the first stage, an attacker has to figure out how to craft a synchronization message that looks legitimate, and that requires them to learn some information at runtime. And then in the second stage, that's where they actually inject that message into the network. And for the sake of time, I'm only going to touch on this second part today. So fortunately or unfortunately, depending on your perspective, it's not that easy to inject a malicious sync message into a TTE network from some non-critical node. And that's because the switches are smart. They know that this message should only ever be generated by a TTE switch. So if it ever comes from some end device, they'll just drop it. So we need some way to trick the switch into forwarding this message that we're actually not allowed to send. And the way that we do that is by structuring PCspooF as what's called a packet-in-packet attack. So the attacker will actually store this malicious synchronization message inside the payload of a benign Ethernet frame, something like an ICMP, ping reply or an ARP reply, typical messages that all of the non-critical nodes are generally allowed to send in a TTE network. And that way, when the TTE switch gets that benign message, they just let it through because it's just a regular benign COTS Ethernet message. And then the remaining hard part of the attack is we now need to coax the switch into stripping that benign header off of the frame and revealing our malicious synchronization message inside. And the way that we do that is with EMI, or electromagnetic interference. So the attacker will actually conduct EMI over the same Ethernet cable that it's communicating over into the switch. So there's no extra connection to the switch or anything like that. And we show in our paper that using this conducted EMI, we can actually induce link resets in other switch ports, like other nearby switch ports. And specifically what we want to do is we want to get a link reset of this second switch port that the message is traveling out of. And the reason we want that is because when the link goes down and comes back up, that act of the link recovering can actually cut the message in half in flight and just result in the tail end of the payload going out on the wire. So if the CRCs are the same, then the resulting fragment that ends up on the wire we can make look just like a synchronization message, and then downstream devices just can't tell the difference. Now, of course, in order to conduct EMI into a switch, we need some amount of malicious circuitry. But one takeaway I want you to get from this talk is that it doesn't take a very sophisticated circuit to be able to get this effect. We've been able to do it with a circuit that only has 5 circuit components. So our prototype circuit fits within about 1 square inch on a printed circuit board, but we're using pretty big through-hole parts and heat sinks and all kinds of stuff. So we think if you were using smaller components, you could potentially get this circuit much smaller than this. And because of that small size, it means that it's within the realm of possibility to hide this sort of malicious circuitry in something like a commercial off-the-shelf device, especially if you consider that because of TTE's isolation guarantees, that means very commonly, even in critical applications, no one is looking for this sort of malicious circuitry. The assumption is, I have the isolation guarantees, I'm safe. People will do things like swab for explosive residue, they'll do burn tests to see if something represents a fire risk, but getting to the level of doing individual checkout of components on a PCB is not very often done. So in order to evaluate the attack, we actually tested it on a real NASA testbed at Johnson Space Center. It's basically a big representative TTE spacecraft network. And we tested it while running an actual NASA simulation of a crew capsule going into lunar orbit. So it's attempting to dock with another spacecraft, and we wanted to see whether having just one malicious device hanging off the network on just one plane and trying to inject synchronization messages was enough to cause this mission to fail. So here you're seeing just a snippet of the simulation while it's running. And on the left, I'm showing results without the PCspooF attack. So just like you would expect in that case, everything works great. The crew capsule in white in the front of us, closest to us, has correctly aligned itself with the white circle of the other spacecraft and then it'll proceed to dock with it. That's the docking interface of the other spacecraft. But you can see things look really different in the case where we're running the PCspooF attack. Actually, just having this one malicious device hanging off the network somewhere was enough to cause the capsule to deviate from its intended flight path by around 200 meters, just due to repeated message drops and losing sync and trying to recover. So it misses the docking opportunity and just floated right past the spacecraft that it's supposed to dock with. And you can actually tell from the picture the capsule is approaching this other spacecraft from the wrong angle. It's coming from the bottom of the other spacecraft instead of the front where the docking interface is. So this mission really has no chance to be successful despite all of the redundancy and fault tolerance that's built into a spacecraft system and that's built into the network. So this work on PCspooF has actually had really significant impacts in practice. We disclosed it to a bunch of different organizations that are using TTE for critical applications, and here I list a lot of them. And since that disclosure, several of these organizations have implemented mitigations and systems that they're designing now to prevent this sort of thing. For example, blocking EMI from being able to enter a network switch is one of the things that we suggest people doing. Another big impact of this work is it's actually driven changes to the TTE standard itself. So this is a statement from TT Tech Computer Technic, who's one of the primary maintainers of the TTE standard, where they said that a mitigation strategy mentioned in our paper was added to a new revision of the standard. So specifically what this will do is it'll make it so that when you cut the header off of a frame in flight, the resulting fragment can never be big enough to be considered a legitimate synchronization message. It's basically increasing the size of a legit synchronization message as big as possible, and that should be able to prevent the attack. So in conclusion, PCspooF is the first attack that's able to break TTE's isolation guarantees, and real systems and lots of different organizations are implementing mitigations to it, and it's also driven changes to the relevant standards. So I encourage you to check out the paper if you want more details, and I'm also happy to take questions. Thanks.
Great talk. I was wondering, couldn't you just flood it with EMIs and cause denial of service anyway without having to craft packets?
Yeah, no. The reason is generally these untrusted devices will only be connected to one network plane, one of many redundant network planes, and that's specifically so that if it just went crazy and electrocuted the thing it was connected to, you'd still be fine. So you need some way to affect the whole network even though you're only connected to a little piece of it.
Okay, cool, thanks.
Very interesting. So you have to be exceptionally lucky for this to work because you don't want to screw up the Ethernet preamble for the synchronization of the devices. You have to hit the header at the exact right moment and leave the rest intact so that the CRC still works out. So can you say something about the success ratio? How many failed attempts do you need?
Yeah, I would say you don't have to be that lucky. Like I said, we can generally get successful injections on the order of every 10 to 15 seconds. So the way it would work is, for example, you would send your malicious frame with the packet-in-packet attack, you turn on your EMI circuit, and generally right when you turn it on, it causes a link reset. So the link of these other switch ports will go down, and as long as your message is somewhere in the queue, when it wakes back up, you can cut it in half. And you can increase your success rate a lot by padding out the space, so you have a really big Ethernet frame, and it's basically all preamble, and you put your malicious sync message right at the end. And then if it wakes up anywhere in there, you can be successful.
Right. I have a question. Is there any open source testbed for this kind of research?
Not that I know of, but we are trying to figure out how to make it more accessible to other researchers who don't have the same equipment. So stay tuned, I guess.
Okay. Thank you so much.
Yep, thanks.
Thanks again.